we need to do our very first, what I'm going to call, grown-up lab experiment. That's right, folks. You know, your time in general chemistry or your time in these other classes, you know, those times have now come and gone. And the reason that I'm saying that is because in those courses, they tend to streamline toward a nice little tidy form with blanks. And you go through and you fill in the blanks with numbers and calculations, and you turn in one form front and back and say, here you go, here's my lab experiment, bye-bye, see you next week. But that's not really how labs are. You know, if you do go on and you get a bachelor's degree or a higher degree in some type of science, especially in a laboratory field, what you're going to find out is that the way that the laboratory is managed, the way that the laboratory is documented, the way that you record your observations and your results are completely different than what a traditional academic institution is going to provide you. So this, my friends, is going to be an insight into a somewhat real laboratory scenario. And this title of the lab is going to be called pH Effects on a Food Preservative. Now, the reason that I say this is going to be a little bit different than some of the others that you've done is because this is going to require a laboratory notebook. Okay? So if you take a look at the lab experiment, the actual procedure part, you're going to see there are no blanks for you. There are no questions to ask at the very end. This is going to be a written laboratory notebook entry for your lab experiment. And it might be the very first time that you have done something like this in a science course. And if so, welcome to real science. Welcome to the real laboratory environment, because folks, this is what goes on. So we need to talk about this lab, and we need to go through the steps of what this lab wants me to do. But before I do that, I want to give you the scenario of this lab experiment. You know, in the very beginning of this procedure that you have probably have access to, or that I've scanned and uploaded into the Blackboard system, it's going to give you a scenario, and the scenario is this. You are going to be working for a food company, and as an employee, your supervisors come to you and they say, hey, listen, we have a competitor, and this competitor is putting a product out onto the market. And what they're using in their food product is something that's called sodium benzoate. Now, by law, they have to put these ingredients on a nutrition label and on the ingredient list. So that way, when you purchase these food products, you know what you're eating. You'll know everything that they have added to that food product. So the next time you pick up something to eat or something to drink, turn on the nutrition label, even on bottled water, folks, and take a look at the ingredients that are included in that bottled water or in that food product that you are eating. So sodium benzoate is an additive that this competitor is putting inside of their foodstuffs. So what your company is basically alleging is that the company that's using the sodium benzoate, it's actually changing when they add it to that food product. So by the time it gets to you, it is a completely different compound than what it started off to be. And legally, they need to be putting on what that compound should be by the time it reaches you, and not what they've actually added in the very beginning. Because this compound is actually changing throughout maybe the packaging or throughout the manufacturing process and so forth. So this is the scenario that they are giving you in the beginning of the lab experiment. You, as an employee with a laboratory company, a food laboratory company, is bringing on a sample of food product that has a big question mark beside of it. And they're saying, listen, they are adding this compound in the beginning. Throughout the process, it's changing. It's not what they actually added in there. So on the ingredient label, they need to be putting what it changed into and not what they added in the very beginning of this process. So that's the scenario. And if you want to read more about the scenario for whatever reason, you might show up in the grade book, it might show up in the lab requirements and so forth, that is where you're going to be able to find that scenario in the very beginning of the lab write-up for you. So I'm going to go through the steps that the procedure told me to do in this lab experiment. And the very first thing that the lab experiment tells me to do is to take a sample of sodium benzoate. So this is what they are using at their company, sodium benzoate right here. So I go to my stock room and I get a container of sodium benzoate, and we ordered this from a chemical manufacturer. So this is the tub that it basically comes in, the container. There's a couple of tidbits of information that's important on labels, such as this one. And one of the tidbits of information that we always write down is the manufacturer's name. So the manufacturer's name is going to be found somewhere on the container. And with this one, the manufacturer's name is going to be called Mallincroft. All right, so it's right here, and you actually see that right on the front. There are many different chemical manufacturers, and this is just one of them. So this allows us to kind of record what we're using in order to report on that maybe a little bit later on. The reason that this is important is because let's say that I use this substance in this container and it does something strange, or it does something weird on me that shouldn't happen, right? It's a little different, and maybe it wasn't my fault. Well, if we can prove that this is a different manufacturer for that compound, there actually could be a problem with the compound that they provided me. It happens, folks. I mean, it's like finding corn in a can of green beans with a green bean label. I mean, it just doesn't pass quality control parameters. And these things can happen throughout a lab. So we always write down the manufacturer's name when we can for that reason. You're also going to see the name of the compound, of course, here. And then at the very top or somewhere on the label, they also do a pretty good job about giving you the formula, the condensed formula of that structure. Now, the next thing that I want to record as well is a lot number. So, for instance, this company makes sodium benzoate, and maybe they make it all the time, but they make it in really large batches. So they take that batch and they divide that batch up into smaller portions that they put in containers like this one, and they send it to me. Well, after that batch is used up, then they will go back and they will make a new batch. Well, there's a reason for that. There's a reason that they record a lot number. There's a reason that they record a batch number. And that reason is because they could actually mess up the process on their end as well. So the lot number is always going to be found on the label. And for this particular one, the lot number is going to be on the side of the container, and you can actually see that up here at the very top. So this is lot 0168 KVSK. So this kind of information is something that we always record in a laboratory notebook when we can. And again, it allows us to track. It allows us to go through and kind of figure out if we do have a problem, was the problem maybe concerning the manufacturer or the batch or the lot number that that manufacturer provided me. So a couple of different errors that can be associated with reagents such as this one in a laboratory. So, in the beginning of the lab experiment, they tell me to take this sodium benzoate, and they tell me to weigh it out. So, I'm going to go to a balance in our laboratory. I'm going to tear out the balance. As you can see here, it's reading 0.0000. And the only thing that I've put on it is just an empty weigh boat, some type of container that I can put the sodium benzoate in. So, it's telling me to weigh out about 2 grams of stuff. So it's going to be my goal to get close to 2 grams. I don't need it exact, but I need to be in the ballpark because all of the volumes and all of the other additives that comes along with the lab is going to be based on that 2-gram sample. So if I weigh out 4 grams instead, and then I use the same amount for everything else after that point, then it kind of defeats the purpose. It defeats the ratios and everything that's required for this lab to work the proper way. So I'm going to take the sodium benzoate and I'm going to open up the sodium benzoate jar. I'm going to put a scoopula in it and I'm going to dig some of this out of there. Here you can kind of take a look at the observations of the sodium benzoate crystal. You can write down whatever observations that you see in the picture, but this was a very fine grain solid, and it was very white, and it was very powdery. I'm not going to say that it was very fluffy, because when I say fluffy, I think of being able to kind of blow on it, and it kind of float up into the air, and it doesn't really quite do that. So I'm not going to say it's dense either, because it did look very light, and it could easily flow and it could easily move. So you can write down whatever observation that you can see from the picture, because this is going to be a requirement of the laboratory notebook. We often write down what we see, so that way if someone else comes along and they do the lab experiment and they go to this jar and they dig out purple crystals and I see white ones instead, then they write down purple. We know that there's an issue with it. We know that that jar maybe has been contaminated and so forth. So that's why we always keep track of observations of things in a lab. All right, so I'm going to take these crystals and I'm going to go back to our balance that had that tear weigh boat on it, and I'm going to just add the crystals up here in the weigh boat, and that's what you're seeing up here in the top of the picture. The final mass of the teared weigh boat with the crystals was 2.0317 grams. So this 2.0317 represents the amount of just the crystal that I'm starting with in the beginning of the experiment. So that is the weight of the sodium benzoate, and that is close enough to 2 grams. I mean, I feel pretty comfortable with that. I'm not going to waste time and try to get 2 grams exactly on the balance. That's not what the laboratory is about, and if you are trying to do that, you're wasting your time when you try to do it. So 2 grams, give or take, and here I've got 2.0317, and I think that's close enough. So if you're happy with that, I'm happy with that too. The other thing I would like to mention is that on the balance, you are seeing an actual bevel that's up here at the very top, and that is basically to keep the balance level. We very often forget to double check this when we use balances in a laboratory, but that is just like a level that you might use at home when you hang a picture or when you hang up a cabinet in something, right? So this bubble needs to be in the center of that balance. And if it is, then that means the balance is actually balanced as far as being level, okay? If it's not, then we need to adjust the feet of the balance because we could have a crooked countertop that balance is sitting on. So all of our balances have that in the front, and that's why that's there. So if I do a close-up of the benzoic acid now that I've weighed it out, this is what it looked like a little bit closer up. So once more, you can make your observations the way that you need to, but that is the close-up version of the benzoic, or the sodium benzoate, the sodium benzoate that we have used here in the lab experiment. So I need to change this to benzoic or sodium benzoate because that is what we weighed out, not benzoic acid. I'm getting ahead of myself. And this is a close up, not a close op. All right. So I'm now going to take that sodium benzoate and I'm then going to transfer that into a container. The reason I do this is because I'm going to have to add some maybe solvent. I'm going to have to add some acid to it a little bit later, and I can't really do that in the weigh boat. I could have taken this beaker over to the balance and just teared it out and added my sodium benzoate directly to it. That would have worked, but just by habit, I just go over and get a weigh boat, and that's kind of where I start. The problem here, though, is that just like before what you've seen in other labs, I had some residue that was left behind in the weigh boat that was here, and I really do need to get that residue out of that weigh boat and into that beaker. That's very important. All of this stuff is going to be stuff that's lost if I do not do that. So when I get ready to add my solvent, I'm going to add my solvent to the weigh boat, and I'm going to give it a good swirl, and I'm going to transfer that into this beaker that has my powder in it. If I don't do that, then this is loss, and that loss could mean company money. And if company begins to lose money, then Tracy does not have a job. So this is something that I always kind of want to take a look at and make sure that my transfers are complete. All right, so the next step of the procedure says that once you transfer that over, you need to go and get a graduated cylinder, and you need to add 10 milliliters of water. So that's what you're seeing here in the picture. That's exactly what I did. So I went and got a graduated cylinder, 10 milliliters give or take. Graduated cylinders and beakers, okay, they're trashy glassware. You're going to hear me say that all the time. They're trashy, trashy glassware. So because of that, if I need specific volumes, and those volumes are very, very important, I'm going to use things that are better than graduated cylinders and beakers. But, you know, for these types of lab experiments where volume is just kind of a roundabout number or an estimate, then as long as we're close, we're good. So right now, nothing has to be exact. So 10 milliliters, give or take a little bit, needs to go into that 2 grams of sodium benzoate, give or take a little bit. All right. So I took that water, that 10 mils of water that you're seeing there, just deionized water. That's what we use in the lab, deionized water. Every single time that we use water, this is what it is. Deionized is not the same as distilled. I always want you to remember that, okay? Distilled is actually heating the water up, and you are killing everything, including bacteria that might be present. And then what you're capturing is truly pure water. Distilled water is actually better than deionized water. Deionized water is only removing ions from the water. These ions are things like magnesium and calcium and maybe copper or lead that might be in your water. I hope not, but it could be. Fluorine and chlorines and nitrates, disinfection byproducts that are typically fluorinated and chlorinated based. That is what it removes. But it doesn't remove any bacteria or any type of pathogen. There's no really heat that's associated with deionized water. All right, so I take that 10 mils of water. I'm going to add it to not the beaker, but I'm going to add it to the weigh boat first. And I give this weigh boat a good swirl. And that swirl, I'll then dump all of that water into this beaker. And hopefully the procedure tells me that that water should start dissolving that sodium benzoate up on me. All right, so when I added the water, I took a look at that beaker to see if, in fact, it was dissolving, and this is what I saw. So in the very beginning, when I added the water, it did not immediately dissolve on me. It took a little bit of time, okay? So this is what it looked like in the beginning. Notice, to me, this looks like that fake snow stuff that you might see at Christmas time in some retail stores. It kind of got a little chunky on me. You can kind of see those larger lumps that are beginning to form. The solution with the water is starting to get a little cloudy. You see a few bubbles, not many, but there's a few there. And all of those are observational changes too that I could report in a lab notebook if it's requested. So I took the beaker and I swirled it around a little bit better. And as I was swirling it around, I started to see more and more of that solid that was getting dissolved. And then eventually what happened is that sure enough, just like the procedure said, all of that solid dissolved up on me. So this was a very good sign that I at least did the very first step correctly. All right. I mean, how can I screw it up? You add water to a solid and you swirl it up and hopefully it dissolves. And it did. Right there is the proof. So here's the side of the container. It does look that there's some cloudiness in here, but my solid is dissolving. So maybe I took the picture a little bit too early, but it was getting clearer and clearer as it sat. If I look through the top of the beaker, this is what I begin to see. I don't really see any large solid pieces. You might see some crumbs is what I'm going to call it here in the very bottom. That wasn't really inside the beaker, though. That was on the bottom of the beaker. It was a little bit dirty from when I set it down onto the countertop. I just didn't wipe the countertop clean before I got started. So that's on the bottom, not on the top. All right, so the next step is going to say, now that it's fully dissolved, you now need to add some acid to that solution. So I went to the laboratory and I have to use a 3 molar hydrochloric acid. All right, so I had to make this stuff. This was not pre-made for me. I actually had to go in and make it myself. And we made it from a 6 molar hydrochloric acid solution. Now, how do we do that? So 6 molar is a pretty standard concentration of hydrochloric acid that we keep in our lab. Concentrated hydrochloric is actually 12 molar. So we take concentrated hydrochloric acid and we dilute it down to 6, and then that way whatever kind of concentration that we need here, and in this case it was a 3, we can make whatever concentration we need a little bit easier from the 6 instead of the more concentrated 12. We do this for safety purposes too. 12 molar hydrochloric acid, that's pretty bad if it gets on your skin. So we just want to limit us handling that kind of strength of acid in a laboratory whenever possible. And here was one of those cases. So I'm going to have to use the magic dilution equation that you learned about in general chemistry in order to figure out how to make the 3 molar hydrochloric acid. So folks, I'm going to come to this screen just to kind of give us a clear page to write on. But I went to the laboratory and got this 6 molar hydrochloric acid. And I needed to make a 3 molar hydrochloric acid instead. It looks like half the concentration, right? So I'm going to give you a shortcut here in just a second. But the laboratory tells me that I need at least X amount in order for me to do my job for this particular lab. But if I'm going to go through this trouble, I'm going to make at least enough to use maybe later on down the road. So what I decided to do was make 100 milliliters of 3 molar hydrochloric acid. So I need to know how much of the 6 molar do I need to use in order to dilute down. What I like to say here is imagine you at a bar, and at a bar you order a mixed drink if you're a legal age of drinking. And when you order a mixed drink, you might take a sip of that and you might say, woo, that's too strong, right? You need to weaken this down. I mean, that's pure alcohol. So you send it back to the bartender and you say, listen, give me some more cutters. Give me some, more pineapple juice or whatever kind of mixer that you like in your drink. But I'm not enforcing you to drink, and I'm not telling you that it's a good thing. But I know if you're 21 or you're older, you probably are going to drink at some point in time. I mean, that's just common sense for most people, right? But again, I'm not telling you to go out and do it. All right, so you send this back to the bartender, and they weaken it down for you, and they give it back. That's exactly what's happening here. We've got a mixed drink that's too strong, and that's 6 molar, and we need to weaken it down, so we need to add more mixer to it, and that mixer for us is just simple old good old-fashioned water. So if I want to make 100 mils in total of a 3, how much of this stronger stuff do I need to make? This is the dilution equation. And that dilution equation is MV equals MV, where M stands for molarity, V stands for volume, this stands for molarity, and of course that stands for volume. Some of the things I want to say about this equation, the volumes here, it can be anything that they want to be. It can be liter, it can be milliliter, it can be cubic centimeter for you nurses. It can be any kind of volume unit as long as it's the same on both sides of the equation. And in a general chemistry class, they typically say M. And the reason they do that is because they talk about molarity all the time. Folks, molarity is great and all, but molarity is rarely used in a real laboratory. So what we've done is that we have modified this equation, and now we like to say C instead of M, where C means concentration, because any concentration will work in this equation. It can be molarity, it can be normality, it can be parts per million, parts per billion, and so forth. It can be anything it wants to be. Again, as long as it's the same on both sides of the equation. All right, so what I'll do is I'll take 6 times x, which is 6x, and I'll take 3 times 100, which is 300. And then I'm going to divide each side by 6 to solve for x. That cancels those out. And 300 divided by 6 is going to be 50. All right, so this is telling me I need 50 milliliters of a 6 molar solution, and I need to use 50 milliliters of that, and I need to put it in a container and then take that volume all the way up to 100 with water. So if I have to write out a statement like this, I'm going to put, well, I need to use 50 milliliters of a 6 molar HCl. Then I add it to a container and dilute, there's the magic word, to the line with DI water. And I can dilute to, and I can squeeze in here, the 100 milliliter line with DI water. All right, so that is how I would prep this solution if I was required to do so in a real laboratory. Okay, I've just done my calculation. My calculation says 50 mils. I'll measure 50 milliliters of that 6 molar out in something like a volumetric flask or graduated cylinder, and then I add water until I get to the 100 mil mark on that container. So that's what I have here in my jar, and it says dilute hydrochloric acid, 3 molar. I put a label on it so I knew what that was after I made it. Now, I don't need all 100 mils, okay? I only need a portion of that, so I'm getting ready to pour that into a graduated cylinder. However, before I show you the next picture, I also want to show you something else, and this is something that other instructors probably won't tell you either. If you look at acids especially, acids and bases both work this way, but acids more so than bases. You're going to see a M and an N that are stamped on concentrations. The N is not the same as M. Okay? The M is going to stand for molarity. And this is what general chemistry tells you most of the time. That is what you work with almost every single time when it concerns concentrations in general chemistry. Again, though, molarity's phony. They've lied to you. They've told you molarity is the only concentration in the world, and that molarity is so important. It's not. Molarity is one of the few concentrations that we actually use on a daily basis. Well, in the acid-base chemistry world, we also have N, and N stands for normality. And what they like to do in the acid-base world is they don't necessarily like to give you just concentration of stuff, but they like to give you the concentration of hydrogen specifically, because we're working with acid, and acid donates proton. So sometimes it might be okay to look at molarity, which is concentration of the molecule, and sometimes it might be better suited to look at normality, which is the concentration of the hydrogen that the molecule gives off. All right, well, in the world of HCl, for every 1 molecule of hydrochloric acid, we get 1 hydrogen from that molecule. So therefore, a 6 molarity is a 6 normal. A 3 molarity is a 3 normal. A 1 molarity is a 1 normal. That is how those concentrations are related to each other. However, if I was using sulfuric acid, like H2SO4, well, these are not equal, are they? There's 2 hydrogens for every molecule that comes around. So if I had a 6 molarity H2SO4, well, I need to look at concentration maybe sometimes in hydrogen-related activity. So 6 times 2 is 12. That is a 12 normal. So for every 1 molecule that comes around, I'm getting 2 hydrogens. My concentration kind of doubles there, doesn't it? And that's what we're seeing here, 6 to 12. So that is the relationship between molarity and normality. And a lot of times they don't tell you that in a general chemistry class, but it's very important in a laboratory science field. All right? Okay, so back to my 3 molar HCl. I'm getting ready to add some of it to my solution that has now dissolved. So I'm going to take some of that solution, I'm going to pour it into a graduated cylinder, and it tells me 7 milliliters or 5 milliliters, something like that. It was probably 5 because my graduated cylinder looks like it's 5 here. All right. So my graduated cylinder's got 5 milliliters of hydrochloric acid on the inside. I'm getting ready to add that to my solution that had that dissolved crystal. And then what happens is here. So when I added the acid, what you're seeing in the picture is that I started to get a little fizz and fuzz on the very top of this solution. And I started to see some white, fluffy crystal that began to form as well on the surface of that liquid. So I slowly added that hydrochloric acid in, and I started to see that fizz and that observational change that began to happen. After I added the hydrochloric acid, I just kind of let it sit, and I just made an observation of it again on what it looked like after I gave it a chance to hang out for a minute or two. And I took a picture of the top of that beaker for you so you can see these crystals that began to form. So notice the way that they look. They are a little bit shiny. They are starting to take on this elongated, kind of jaggedy looking crystal, which is something that we often like to see in a laboratory. It makes us feel good about the crystallization process. And then finally, to the side of the beaker, I started to see more fluff. I started to see stuff that looked like cotton or cotton candy in a way again. So once more, these are the observational changes that began to happen. It did look a little bit different than my starting product, as you can tell from the very beginning. I took the beaker, I tipped it over to the side just so that you could see that there was a large amount of crystal that had formed at this point. There seems to be very little liquid that's left in the beaker. And that's just simply due to the large amount of crystal that I'm starting to get in this beaker for me as a product. So very, very small amount of solvent that's still left in there that I could physically see. Here is another picture now that I've let it sit for a couple of minutes from the top down, and that just really gives you a viewpoint of the surface of that liquid and really how much different this crystal begins to look from my starting product in the very beginning. All right, so the next step of the lab experiment basically told me, now that you've done this, you need to check it with a piece of pH paper. The reason is because we wanted to acidify that solution. That was the whole purpose of adding the hydrochloric acid, right? I'm adding hydrochloric acid. I want to make sure it's acid. Otherwise, why would I add the hydrochloric acid? I mean, that makes no sense. So this step is just confirming that you did go acid enough, okay? So I took some pH paper. Fisher brand was the name of our pH paper. And this pH paper does a really good job between the pH ranges of 0 to 14. Okay, so on the back side of this container, or the vial that all my pH paper's in, I'm going to see a color code just like before, and this color code is 0 to 14. So 0 to 14 is going to give me some colors that will go acidic to basic. So when they say acid, in the lab directions, they're telling me pH of 2 or below. All right, so the colors that I want are mainly this kind of orangey, tangerine-y looking color to more of the reds that I'm seeing over here on the left. If I see more of a yellow tinge, greenish, or bluish, then I am not acid enough. So that first initial hydrochloric acid needs to go even more. And that's the whole purpose of this step. So I popped the top of the pH paper. I took the pH paper out. It comes into a strip like this. I don't need them all. I just need one strip of paper. That's it. It is normal to see this kind of tinge of color that's associated with the paper. Other people have touched the paper. The acids and everything on your fingers will get onto the paper. So over time, they do begin to change on me a little bit, but it's not bad, right? And it's cheap. So if they do get contaminated, I hope they don't. But if they do get contaminated, we trash them. We just get a new vial. No big deal. So I'm going to take one sheet or one strip of paper from that ream, and I laid it down onto a piece of paper towel. and I brought it nearby to my beaker with my slush that's on the inside of it. And I took a stirring rod and I dipped my stirring rod into that solution, and then I dabbed that stirring rod onto the pH paper. All right, folks, a dab a do ya. That's all that you need, a dab a do ya. All right, so that dab is giving me this orangey color. So this told me that that first addition of hydrochloric acid maybe was not enough. I needed to go a little bit more. All right, I need this to be really, really acidic. So the directions told me 2 or lower. So I compared that color to the pH vial, and it looks like I was pretty close to this pH of 4. So I was acidic, which is a good sign, but I wasn't acidic enough. I need to go a little bit lower than pH of 4. So that means I need to add more acid. All right, so whenever we do this, it's very important that we somewhat keep track of everything that goes on in the lab at this point. So I need to go on and I need to add more acid, but I also need to record down how much acid I exactly had to use, so that way the next person that does this experiment can keep track of what I did. Because if I had to do it, there's a chance that someone else would have to do it as well. So in the next picture, what you're going to see is me going back to that 3 molar hydrochloric acid jar. I took the disposable pipette, sucked up some of the hydrochloric acid on the inside, and then I went back over to my container that has my solid in it, and I added drop, 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 drop into this beaker. All right, so what I do is I normally do like 10 drops at a time. So I added 10 drops in this case, and 10 drops of acid. I put my stirring rod back in, and then I stirred it one more time, and then I went back to my pH paper, and then I wanted to recheck it. When I went back and rechecked it, then here is my color. So notice that it became more orange, which is another good sign, but I'm still not really pH or 2 below. I would like to go a little bit further than this. So I could maybe add some more hydrochloric acid. The directions told me pH 2 or lower. So even if I go super red, I'm still going to be okay. And I want to be safe than sorry. All right, so what you're going to see here is just my setup. And I'm going to show you this video just so you can visually see what was going on in the lab during that time. So I'll pause myself here and I'll play myself in the PowerPoint presentation. All right, guys, so here is the setup for the sodium benzoate lab. Just a quick video on what's happening right now at this moment. I've got my 3 molar HCl that's here that I'm adding to my solution because the directions tell me to make sure that I go acidic to a pH of 2. And right now the initial conditions, as you can kind of tell here from the pH paper, is really going to peg at about 4. And I've got a close-up picture on that. So we needed to add more hydrochloric acid to the solution. So I took the 3 molar HCl that's basically here with the dropper. I added a few extra drops inside of this beaker, and when I did that, this slurry got even thicker, and now I'm getting ready to test this sample one more time. So I'm just going to take my stirring rod, and with the stirring rod I'm going to come over to my pH paper, and I'm just going to put a dab onto the pH paper, and notice that that color now is a much deeper red and not as tangerine-y looking. So if I try to match my pH paper up to that particular color, it looks like now I'm in this vicinity here. So now I am lower than pH of 2, at least more so than what I was before. So I'm going to keep adding maybe a few more drops. Currently I'm at 10. I might add 5 more just to be safe, and then we'll take a look at the color when I do that. But there is the setup of the pH addition. So we are controlling the pH of that solution at this moment in time. Okay. So here was that picture that's a little bit close up of the second drop. I told you that I was going to go back and I was going to add 5 more drops of solution, and that's exactly what I did. So this brings my total to 15 extra drops of hydrochloric acid. I then went back, I dabbed it onto the pH paper, this new strip that you're seeing here in front, still on that paper towel, and I took the stirring rod and I touched it. And that's basically the color that I ended up getting after the addition of those 5 extra drops. Once more, I went back to the color code and I try to match it up, and it looks like now at this point I'm in the realm of a pH of a 1, and I felt pretty comfortable with this because, again, the lab said 2 or lower, and as long as I'm lower, I know that I'm good. So I would rather be red than on the verge of the 2 as far as color goes, again, just to be safe. So the next part of the procedure says, now that you've done this, you now need to prep an ice water bath. So basically, here's a picture of our freezer where we like to keep our ice trays and some of our ice cubes. So I went to the freezer and I took out some of the ice cubes and I put it into the beaker that you're seeing into the picture on the top rack. Sometimes if I know that I'm getting ready to do an ice bath, I will like to put the beaker in the freezer. So that way the beaker and the glass it comes in is actually super cold too. Again, I'm not encouraging you to go out and drink, but for if you are a drinker and you enjoy beer sometimes, beer comes to you in a super, super cold glass, it seems to be a little bit better for you and you enjoy it a little bit more. So that's what I do in the laboratory. If I know I need an ice water bath, why do I want a warm or a hot beaker in order to do an ice water bath in? So I put my beaker into a freezer. I let it sit in there for a few minutes before I need it. I then went, got out some ice cubes, put it into the beaker, but that's just a beaker of ice. That is not an ice bath. So I added some water to that beaker, and there, ladies and gentlemen, is my cold water bath that I need for the lab experiment. Okay, so in the lab experiment, it tells me that once you get these crystals that are acidified with a pH lower than 2, you then need to take those crystals and you need to put them into an ice water bath. And it's very specific on temperature with me at this point in time. So here I've got another video. I just would like to show you the ice water that is beginning to go on, so that way you can kind of get caught up with the process. So let me pause myself for a minute and play myself in the presentation. All right, guys, so in part of the procedure, it tells me to cool the solution until it gets 10 degrees or below. So I've used my LabQuest 2 device right now. I could use a normal thermometer if I want, but this was convenient. It was already out, so I just decided to use it. So right now it looks like my temperature is at 11.2 degrees. If I feed the cord through and kind of let you take a look at what's happening over here, I've got the thermometer probe down into my solution of my new substance that has formed, or what I think has formed at this point in time, and it's just really sitting down into a beaker full of ice water. So right now the temperature is reading about 10.7. When this gets below a 10, then I'm going to take out the beaker and then I'm going to filter this sample through a Buckner funnel. That way I can report a amount of product that I think that I have made, and we can calculate some theory yield and that kind of stuff on it. So here we are at 10 degrees, and I'm going to let it get a little bit colder before I take it out, and then in the next few pictures you're going to see the process of the Buckner funnel all over again. So now you know why we did recrystallization, because it introduced you to the Buckner funnel when you did that lab experiment. Okay, so as you could tell in that video, my temperature probe was reading colder and colder and colder. And even at this point at 9.4, it was below a 10. But I did leave it sit in there a little bit longer, just again to be safe than sorry. That's just normally how I roll. So I actually took the beaker out when my temperature read 8.4. So this allowed me to take my beaker out, set it onto the countertop. I knew that it was still cold and it might warm up a little bit when it comes comes out of the ice water bath, but if I get it cold enough, then so what if it does? It's still going to be super cold and my crystals are still going to fall out of solution the way that I need to. All right. One of the things that we also like to do here in a lab is not just record temperature, but also record times. So that's what you're seeing here. How long did I actually keep it in here? Well, I put this actually in about 9:38 a.m. in the morning. I know I was crazy that morning when I got up and went out to the lab to do this experiment. Who does that so early in the morning, right? So 9:38 is when I dumped it into this beaker. And then when I took it out of the beaker, you know, I keep track of the time. How long did it actually stay in that ice water before I took it out? So I took this out at about 9:46 a.m. with what I jotted down onto my own personal lab notebook. And that gives you an idea of how long this beaker actually stayed in there during that time. All right, so I removed the beaker, let it sit on the countertop. In the meantime, what I did, I knew I was going to have to filter it. So I went back to our filtration drawer and I took out this Wattman filter paper again. So once more, these pieces of filter paper are made for our Buchner or our Buchner funnels. However you want to say it, tomato, tomato, it doesn't really matter. And this is what I needed in order to put into that funnel so that way I could capture my solid that just formed in my beaker. So as in most cases, when we use a piece of filter paper, we want to make sure that we go to a balance and we want to make sure we get the weight of that filter paper, right? We need the mass of it. So I went back to my balance. I made sure that it was tared out, and it was, as you can see on my screen, 0.0000. And then I placed the piece of filter paper onto that balance, and then I recorded the mass of that filter paper. And that was a 0.2074. So that is the mass of the filter paper. And the reason I do this is because solid's getting ready to go on top of it, right? So if I'm going to get the mass after I get the solid on the filter paper, if I don't have the mass of the filter paper, how do I know how much solid that I recovered? So these masses are very important. So this is what I'm going to tell you whenever you're in the lab. If in doubt, always take a mass of something. Okay, if you don't need it in the very end, you don't need it. And you just trash it or you don't use it. No big deal. It's going to take just a couple of seconds in order for you to get a mass. However, if you need a mass and you were unsure that you needed it and you questioned it and you didn't record it, and then you get to a point later on in the lab experiment and you really needed that mass that you didn't take, then there's a chance that the rest of the lab is going to be messed up for you. So all of that time is going to be lost because you might have to go back and you might have to redo this all over again. So who wants to do that? I don't, and I know that you don't either. So make sure that you get masses of things. If you are unsure if you need it, take it anyway. That's what I tell people. Take it anyway. It doesn't matter. So vacuum filtration, here's the vacuum filtration setup. The vacuum filter or the filter flask is down here to the bottom. And then my Buchner or Buchner funnel is up here at the very top. And I'm getting ready to put this filter paper here at the very bottom into the top of that Buchner. And I need to seat the filter paper. So again, I'm going to take my squirt bottle and I'm going to squirt the top of that filter paper. And that way it will seat itself up against the Buchner funnel and it will capture all of my solid and not allow my solid to go through the holes of the Buchner funnel. So some of the questions that I put up here on the slide, do you know the pieces that are required? Because this could be a test question, right? So Buchner funnel up here at the top, a filter flask that's down here at the bottom, and an aspirator, which is basically the water faucet that's sitting behind this Erlenmeyer flask or the filter flask. So aspirator is what that is termed. And also, can you explain how it works? So the water flows through the nozzle, and the water flow creates suction or pressure, and that will pull the air through the filter paper and into the filter flask. My solvent will be captured down here in the bottom, and the air will be sucked out, and the air will continuously be pulled through that filter paper and my solid to help dry it out maybe a little bit quicker in the aspiration setup. All right, so the picture of the Buchner or the Buchner funnel is here. So those are my holes that I do not want any of my solid to go through, but I do want my solvent to go through it. And in this case, it's just really acidified water. That's all that it is. All right, so for those of you that need a little bit of more visual, here's a video of the filtration process. And once more, I'm going to cut myself off and turn myself back on. Okay, folks, so we are ready for the vacuum filtration or the Buchner funnel step. I'm getting ready to turn this filter on. I already have a piece of filter paper in the actual funnel itself, but I told you that we always have to seat the filter paper. So the filter paper is on the inside. I've got a squirt bottle full of DI water here. I'm just going to squirt this water on top of that filter paper. I can make sure that all of the holes are covered up with the filter paper, and they are. So I'm just going to let this run, and then I'm going to go grab some cold water out of the freezer because that's what we have to wash all of these crystals with that are right here. So I'm going to go grab that ice water. I'll come back and I'll take a few more pictures of this process as we begin the filtration. Okay, so the lab experiment told me that once I get my crystals on the filter paper, I then need to rinse those crystals with ice cold water. And the question is why? I mean, is that really necessary? Can I just use like distilled water or deionized water that's just sitting out on the counter? And the answer is no, you can't. And the reason is because we put this in an ice bath for a reason, right? I made sure that when I put it into an ice bath that I kept it cold, 8.4 degrees. That was very specific in the lab document. So I don't want to use room temperature water. And the reason is because if I do use room temperature water, when I go through and start squirting and rinsing my solid on the filter paper, there's a chance that that room temp water will start dissolving it. Why would I want that to happen? I just made moves to get a solid. I recorded temperatures. I recorded times. I wanted to make sure that I did get crystal and enough of it. And if I use room temperature water, there's a chance that those crystals would dissolve on me. And all of that work was for nothing. So why would I want to do it? So that is why the lab tells you to use ice cold water to rinse these crystals off. So what I did is that I took deionized water that we had in the lab. Once again, I put it into our freezer to get it super, super cold. And then I actually unscrewed the top of the DI water bottle and I put some ice cubes on the inside of it and I gave it a good shake. And then I took that water bottle out to the lab with me. So that way, by the time I get to use it, it is still cold straight from the freezer. Just like a hot summer day, having a nice, refreshing drink by the pool. That is what these crystals want, and you have to give it to them. So in this picture, you're getting ready to see me pour these crystals through the filter paper. So it was very thick, it was very slushy. I wasn't actually able to get everything out of the beaker in one fell swoop. Some of it did come out, as you can see here in the very bottom of this filter paper, but not all of it did. There was some that was still left in the beaker. So I took that ice cold water and I squirted some inside of that beaker. Remember, folks, it's all about transfers. Transfers are very important. So I took ice cold water, squirted it into the beaker. If they want me to rinse the crystals with ice cold water, it's perfectly okay to rinse everything else with ice cold water too, right? That makes sense, I hope. So ice cold water into the beaker. I gave this beaker a good swirl, and then I dumped it back out. And I still had remnant that was left over in the beaker. Look how much stuff that was still here. So I had to do it again. And again, this is a problem with a transfer. So I added more ice cold water around the sides of the beaker. I gave it another really good swirl and I dumped it all back out onto the filter paper, and I wanted to make sure that at this point all of my crystals were transferred over completely to that filter paper, and they were. So here I'm basically going to show you the next step of the process. Okay, so my crystals are filtered. All of my water has now went through the Buckner funnel into the bottom down below. It tells me to rinse it again with ice cold DI water. So again, that's what I've got from the freezer here. I'm just going to basically squirt some cold water on it. And the reason is because in warm water or room water conditions, these crystals have a tendency to dissolve. And I don't want to lose any of that product, do I? I want to keep everything that I can. So I've just quickly rinsed it with some DI water. I'll let all of that water drain and it can be caught into the flask down below. And I'm just going to let the aspirator run for a few minutes before I transfer this piece of filter paper into my oven on the back side of the room. Again, you'll see some pictures of that process as well. I've got my oven already on. It's already heated up to about 100 degrees, which is good because I need to dry this and I need the water off. And it can't happen unless I get it above 100. So in the oven it's going to go after I let the air to continue to run through it for a few more minutes. Okay, so after that part, I took the filter paper out of the funnel and I placed it on a watch glass so I could take it to the oven. But I wanted to show you that some of that crystal was still left behind in the Buckner funnel. I did take a scoop or a spatula and I tried to scrape all of this off of the sides and onto that piece of filter paper. Again, I don't want to lose any of this because all of this is percent yield. All of this is product that I could recoup and reclaim and recover and report. So because of that, I don't like to leave anything behind. So I try to scrape as much as I can out of there before I just finally give up and say, well, you know what? I know that we're going to lose some. That's just a part of the process. We know that this is the case. With every transfer, we're going to lose some material. So sometimes there's just no way around it. But I at least wanted to show you that and highlight that all of these transfers are going to be very important. In addition to that, the scoop that I was using, crystals also stuck to that scoop. So this is another kind of problem area that we always see in a lab. Sometimes there's just no way around it. You can't get everything off, folks, no matter how hard you try. If you try to take another scoop and try to scoop this off of that scoop, then it's going to get onto your other scoop. And there's a chance that it will never leave that one. So you're just now juggling back and forth between the tools of the laboratory. So if I zoomed in a little bit more, you can actually see how much crystal was still left on that scoop. It clung pretty well to the surface of the scoop that I was using. So once more, I just didn't really bother with the rest of it. It looked like I had quite a bit here, and I felt pretty comfortable that I didn't majorly lose anything else throughout the process. So here's the product on the filter paper, and I put it on a watch glass so once more we can go to the oven and put that watch glass on the oven rack. If I put the filter paper directly on the oven rack, we have a problem because it will char and burn the filter paper. And that is why I never do that. So I always put it on a watch glass when I take these products to an oven to dry. So here was a picture of the oven that we used. Again, we have a number of them in a lab. This is just the one that I decided to pick. I had already cut it on, so it was already preheated by the time that I needed it. And if I zoom in and give you a closer picture of the oven settings, because that's also something that we might like to write down, I've turned the oven on over here to the right-hand side, and I've dialed it up to about a 3. And that 3 is a pretty good sign for us as far as our ovens go, that we are about close to 100, give or take a little bit. So I took a picture of the thermometer from the top, and as you can see, we were above 100, and that was a good sign because water will not go away unless I'm over a 100. So here I'm looking at like 101 maybe. So I'll put my product in the oven, I'll let it sit in there, I'll let it dry, and then I'll go back to it, I'll take those out, let it cool to room temperature before I do a mass of it. We cannot weigh hot things in a laboratory. We need them at room temperature because it does affect the mass that is associated with the compound, right? I need to let all of that to cool, and the reason is because of the air currents. Air currents flow on top of my stuff. Think of your head, and above your head is a column of air that constantly pushes down on you, and your neck is strong enough to stay up. So the same kind of thing happens on tops of these solids that we decide to weigh in a balance, and we've got to make sure that everything is cool to get an appropriate weight. So this is what the crystals look like when I took them out of the oven. All right, now I need to give you the time that I kept them in the oven. So if I go back to my notes, I'm seeing that I put this stuff in the oven at 10:27 a.m. in the morning, and then I went back and I took it out at 10:52 a.m. that morning. So that will give you an amount of time that's associated with keeping the crystals in the oven until I knew for sure they were dry. I did check on them during this time, and when I went back to check on them, I could visually see the filter paper still wet. I could also visually see the crystals still wet. I kind of touched the sides of the filter paper, the bottom of the filter paper, took it out, just kind of made some observations on if I thought it was truly dry or not. And at 10:52, everything looked, I'm not going to say crispy, but everything looked like all of the residue of water has been driven off at this point. This kind of makes sense. We were at 101 degrees, so water boils at 100. So that's when the evaporation would maybe start to take place. So I knew that it was going to take a little bit longer, and that's how much time it actually did take. All right, so I went back to the balance, and when I went back to the balance, I put that filter paper with my product on it at this point, and I got a 2.3248. So keep in mind that the 2.3248 is the mass of my product, plus the mass of that filter paper that's also there. So in order to get the mass of the product, hopefully you'll know how to solve for that. You simply just subtract the two. That's all that you need to do. So 2.3248 minus the mass of the filter paper that was just the filter paper only, and that will give me the mass of the product that I have reclaimed at this point. All right, here's a final close-up picture of everything that was completely dry after I had weighed it and brought it back to the lab bench. You might need to make some observations of that, and if so, then there you go. That's what the stuff is going to look like. So a couple of summary items that I would like for you to keep in mind. Number one, my benzoic acid, which is what this company thought that this product would turn into, I had true benzoic acid in the laboratory. And I actually forgot to take a picture of that container with the label. Normally I do that for you because this is a testing piece that we have to do. So as far as the label goes of the benzoic acid, this is going to be an NA for the label. We do have it. I forgot to take a picture of it that day. I just went ahead and made the presentation though, and in the laboratory notebook you can just say NA or not available. But that benzoic acid had a melting point of 120.6, okay? And that should be a degree up here, not that circle down below. So 120.6 degrees. The sample that this was, the final product, I put this in our melting point 50 system, our Mettler-Toledo MP50. So you know how we use that instrument. This was done in another laboratory so far. So you know the directions on how to use the melting point system. This is also something that we like to put in our laboratory notebook. How do you actually use pieces of equipment? So this does include turning it on, telling me what buttons you have to push, telling me what settings you have to make. So the settings on the melting point 50, because I knew that this was possibly benzoic acid, because I knew that the melting point of benzoic acid was around 122, then I focused in on that number. So what I did in the melting point system is that I started this at 100 degrees Celsius for start temp, and I did 135 degrees as an end temp. And my heat rate was 10 degrees for every minute. So this was my rate. This is also something that I like to write down in a laboratory notebook. Again, I forgot to take these pictures and upload them for you, and I apologize, but this was done. I just got into the middle of a couple of different labs at one time, and I was trucking on because I was getting things done and I was happy. So it just slid by me during this time. So 100 to 135, 10 degrees for every minute. And the average, I'm just going to go ahead and give you the average. I did 3. The average of those 3 samples that I received was 121.4 degrees Celsius. All right. So this was the melting point of the sample that we made in the lab. And this was the melting point of actually benzoic acid that we ordered and had it shipped to the lab. All right. So the melting point error is going to be something that you're going to have to write down in the laboratory notebook. So the melting point error is basically the theory minus the actual. Okay. So the theory is what it should be textbook, and the actual is what it actually is when you did it in the lab. So again, I hope that makes sense. I think it does. And then you're going to divide that by the theory. All right. And because it's percent error, we have to multiply by a 100. So this is how you're going to calculate the melting point error for that product. I could do it for the benzoic acid as well, but I think that the lab directions only want you to do this for your sample, not the sample and what we would call the stock. So this is what we would call the stock benzoic acid. Hopefully, if this stuff is benzoic acid, these two melting points would be similar. And they are, 120.6 and 121.4. So this gives me a good idea that my sample or my product is actually benzoic acid because the melting points are pretty close. But the calculation is only going to involve the sample here, and that's it. All right. Another type of calculation that you're going to have to do for this lab is theory yield and percent yield. All right, so here's a review of general chemistry. We're going to have a starting mass or gram of my sodium benzoate that I used in the very beginning of the experiment. And I put that over 1. This is the way I set up dimensional analysis every single time. Okay? I take my given, and that given is a value they give to me or that I get in a laboratory. And that given is the start mass of sodium benzoate that we used. All right, so gram of Na-benz is how I'm going to write this. All right, so grams of Na-benz on top, gram of Na-benz on the bottom. That is the way that these cancel out every single time, and we have to get them to cancel out. I'm getting ready to set up what we call dimensional analysis here. And I need to transfer that over to mole of Na-benz. All right, so this is why. All of these different molecules, it's like different countries. They all speak different languages. So there's got to be a common language that everyone will understand. All the molecules understand the language of mole. So if I am trying to take sodium benzoate, which is one type of stuff, and I'm converting that over to a new type of stuff, the only way that I can do that, compare the two stuffs together, is to talk common language between the two. And that common language is mole. All right, so I'm not going to do anything with numbers right now. I'm only going to worry with my unit. So once I get to mole of sodium benzoate, this is the language that sodium benzoate talks, and that's good. Well, mole of sodium benzoate has to go down here in the bottom. Well, this is not my product. My product we thought was benzoic acid. That's what the company told me. That's why we did the stock benzoic acid crystal. So I need to get mole of benz-A, which is going to stand for benzoic acid. Now that's speaking the common term. Okay, when that happens, I can't weigh out mole on a balance, can I? Absolutely not. I can't weigh out mole on a balance. My balance gives me gram. It doesn't give me mole. There's no unit on the balance for me to change to report moles because it's all different based on the compound. So once I get moles of benzoic acid, I need to get to gram of benzoic acid. So, just like before, mole of benzoate on top, mole of benzoate on the bottom, and I need to go to gram of benzoate. And this will tell me what we call the theory yield of what I should have ended up with. Now I need to plug numbers in. So I know the number that goes here. This is the amount that we actually used in the lab when we did the lab together. Gram and mole are related through formula weight. Formula weight unit is grams per mole, people. So there is a relationship between those two. So I need the formula weight for sodium benzoate. And they give me that in the lab procedure. Only thing I have to do is look in the lab document and get the formula weight. And that formula weight is going to tell me a number. What is that number? Have you looked? If not, I'll give you a hint. That number is going to be found in a table of physical properties in your lab procedure. Anytime we do these types of calculations, anytime, that's where you're going to be able to find these values. So if you have that in front of you, go to that table where the procedure's at, look at that table, you're going to find sodium benzoate, and beside of sodium benzoate, you're going to find a formula weight. And what do you see? 144.1 grams for every 1 mole. That is what formula weight stands for. All right. The next step, mole of my starting stuff and mole of my product. This is a 1-to-1. I'll show you how I know that in just a second, but it's a 1-to-1 relationship. So 1 on the bottom, 1 on top. And then finally, we have moles of benzoic acid, and we need to know how many grams of benzoic acid. So once more, I need formula weight. Formula weight tells me grams and moles and how they're related. So I go back to that table, I find benzoic acid. Beside of benzoic acid, I'll find a formula weight. And what do you see? Well, 1 mole of benzoic acid is 122.1 grams of benzoic acid. So there's the calculation for theory yield, okay? Theory yield is taking my starting amount and trying to calculate how much I would end up with here in the very end of the lab experiment. So I need to take my starting amount, I need to times it by 1. If you want to do that, leave it out though. Anything times or divided by 1 is the same number. So why would you do it? It's just extra steps. So take your number, divide it by 144.1, and then multiply by 122.1. And you'll get a number over here. And this is going to be your theory yield. All right? Your percent yield, what is that? All right, well, percent yield is going to be another calculation. And percent yield is very similar to that melting point error. You're going to take the theory of what you should have ended up with from the last problem that we just talked about, minus your actual. This is what you actually got in the lab. It's probably not identical to the theory. We're not perfect. We're probably always going to be lower than the theory yield. If we're higher than the theory yield, it probably means that we have extra water weight or something, okay? We haven't really dried it out enough. And we're going to divide that by theory times 100 because we're talking about percentage. So once more, what it should have been minus what you got, divide it by what it should have been, times 100 to get percentage, and this will give you percent yield of your product. Once more, in these laboratories, we typically like to see labs that give us about 60% or higher as far as percent yield goes. If we do this, then this is a very good sign that we did our transfers the proper way. We let the reaction to go to completion. We have very minimal byproducts in the end result of this process. So it's a very good sign that we did a pretty good job of recovering and making that product that we were after. All right, so those are a couple of calculations that's going to be required for the lab notebook. And you'll see those listed on what I call the grade sheet. We'll talk about that in a separate video. But this is at least the motion of the calculations that you're going to have to start doing in that lab notebook for me. All right, so here's your setups, especially if you haven't seen this in a while. If it's been quite some time that you've taken general chemistry, you forgot how to calculate theory and percent yields, then this will be a good review for you, or at least a start of a review for you. All right, so there you go. There's the process of calculating theory percent yield, and there's part A of that first laboratory experiment that we have to do in our laboratory notebook. Okay, so you're going to see another video that's attached to this one. In that other video, we're going to talk about part B, and part B is really completely separate. It's about density. So what do we do as far as density goes? How do we handle those types of calculations and so forth? So that's going to be treated separately in its own video, so that way all of the pictures and the videos and the calculations can be cohesive together. So here is part A of the sodium benzoate lab. All right, so here's your data. There's an example of how to do some of the calculations. You'll go back, you'll write some of this stuff up in your laboratory notebook, and once more, check the grade sheet. Make sure that you are writing in the things that you need to write in to the grade sheet.